Okay, in this video we're going to talk about soil mineralogy and grain size ranges in soil. So I've drawn a line here representing gravel, sand, silt, and clay. And of course the dividing line between gravel and sand is the number 4 sieve, and between sand and silt is the number 200 sieve. The number 4 sieve is 5 millimeters, the number 200 is 74 microns or 0.07 millimeters, and clay minerals are smaller than 0.002 millimeters or 2 microns. Clay minerals are characterized as being mostly clay, so clay soils have mostly clay minerals, and the particle shapes are platy. They have very thin particles with a lot of surface area. By contrast, the coarse-grained particles larger than 2 microns are mostly non-clay minerals, and they have a bulky shape. So rather than being like flat plates, they're more like spheres or cubes or something like that. Bulky particles are really controlled by gravity. The surface area for these particles is so small relative to their mass that really they can be thought of as being inert in terms of electrochemical surface interactions. So gravity and the surface roughness and shape really controls the behavior of these particles. By contrast, platy particles have a really big surface area relative to their mass. So all of those little electrochemical charges that happen on the surface of these particles become pretty large relative to the mass of the particle, and we can't ignore those electrochemical surface interactions anymore when we talk about the behavior of these clay minerals. Let's move on now to talking about specific surface area. So the definition is the surface area divided by the particle mass. Let's do a quick example. If we have a cube that has 10 millimeters side lengths on all 3 sides, so a perfect cube, and we assume that the specific gravity of the material that the cube is made of is 2.7, a common specific gravity for Earth materials, then the mass of that cube comes out to be 2.7 grams. That's just a simple volume calculation. The surface area is equal to 6 sides multiplied by 10 millimeters times 10 millimeters. That comes out to be 6 times 10 to the minus 4 meters squared if we do the conversion from millimeters to meters squared. Usually specific surface area is in units of meters squared per gram, so it's convenient to make that conversion. So computing the specific surface area now and using the term SSA to represent it, we have 6 times 10 to the minus 4 meters squared divided by 2.7 grams, which is 2.2 times 10 to the minus 4 meters squared per gram. This turns out to be a pretty small specific surface area. We wouldn't expect surface interactions to be a contributing factor for this particle. Now let's say we take that cube and cut it in half on each side. So now there's 8 little cubes, same mass, same overall side length, but each little cube is just half as big on each side length. Now the surface area turns out to be 10 times 10 to the minus 4 meters squared. It's double the surface area from before. So the specific surface area is also doubled, 4.4 times 10 to the minus 4 meters squared. Let's say that we further cut this cube so that the side lengths are just 1 micron. So we've gone from 10 millimeters down to 1,000th of a millimeter, and the surface area now goes up to 6 meters squared. And the specific surface area of that material would then be 2.2 meters squared per gram. That's still fairly small. Montmorillonite clay, believe it or not, has a specific surface area as high as 800 meters squared per gram. If you were to spread out 1 gram of Montmorillonite clay, you could cover an entire football field with it.